This is a two-way stand-mount speaker, a 7-inch woofer, a 1-inch dome tweeter, and a bass reflex cabinet, designed end-to-end with an AI coding agent as the engineer's collaborator. It started as a hand-drawn cross-section, a Dayton Audio RS180-8 woofer, an RST28A4 tweeter, and a vented enclosure sized to fit them. From that sketch, a parametric model. Every panel width, every driver position, one block of numbers driving the whole geometry. Once it's glued shut, you'll never see any of this again. Inside the shell are 6 shapes, each solving one specific problem. Positions are measured as height above the floor in multiples of 18 millimeters, because the whole cabinet is built as a stack of 18 millimeter layers. Here's what's actually in there. The slot in the front baffle is a hole with a tube behind it. The air in that tube bounces on the springiness of the air sealed in the box, and near 36 Hz, it swings hard enough to do the bass output for you, while the woofer cone itself barely has to move. Push much below that frequency, and the trick reverses, working against the cone instead of with it, which is why a 25 Hz high-pass filter isn't optional. When the woofer is working hard, it turns the sealed cabinet into a pressure cooker, up to 390 pascals inside the box. The tweeter's thin rear housing was never built for that, so it gets a sealed wooden hut of its own. Cabinet air passes over, under, and around it. The tightest clearance anywhere in the cabinet is here, 3 millimeters between the woofer's rear body and the chamber floor. The largest radiator on this cabinet isn't a driver, it's the sidewall. A big flat panel is a drum skin, and left alone it rings at 217 Hz, right in the woofer's pass band. The fix isn't a thicker panel, it's a shorter one. A window brace across the middle halves the span, pushing that resonance up to about 514 Hz. In a laminated stack, the brace isn't a glued-in shelf. It's the same continuous piece of material as the wall itself. Sound bouncing between 2 facing walls inside the box piles up wherever a half wavelength exactly fits the gap. This cabinet has 3 such gaps: height, depth, and width, so it wants to ring at 3 different notes: 400 Hz, 489 Hz, and a band between 892 and 1200 Hz for width, deliberately smeared by the curved side walls rather than left as one sharp tone. A dead-end slot cut to the right length resonates at exactly the note you want to remove, and sitting in the wave's path, it soaks up energy at that frequency. 2 of them sit in the rear corners, tuned to the 400 and 489 Hz modes. They cost under a liter of volume combined and are free to cut, because unlike a driver bore, a vertical slot is just another shape on a horizontal layer. But bare, a trap is a needle. It mostly just stores energy and hands it back. A loose wisp of wool in the mouth is what actually turns that into heat. There are 2 ways to absorb sound, and they want opposite locations. A resonator needs pressure, so it goes where pressure peaks, the corners. Fluffy material works by rubbing against moving air, so it goes where the air moves fastest, a quarter wavelength away from that same peak. Line the walls, don't pack the box. Dense fill drags both traps and the port itself out of tune. Knowing where the wool should hang is one problem. Holding it there through a glued-shut box is another. Dowel pockets, laced with cord through the brace, do the holding, and every part of that joinery has to be cuttable from flat sheet and installed through the woofer bore after glue-up, since nothing else stays open. High notes are small compared with the front panel, so it acts like a wall, and they fire forward off it. Low notes are far bigger than the whole cabinet, so they just bend around it. Losing that wall below 479 Hz costs about 6 decibels, half the pressure at your ear, so a speaker that measures flat in isolation is bass light as a whole, and the crossover has to turn the treble down to compensate. The port tube was designed as a spring and weight for the bass, But a tube is also a flute. It has a note of its own, up in the mid-range, with a clear path straight out the hole. Here, 556 Hz. When the corner traps took nearly a liter out of the box, the port had to grow to hold its 36 Hz tuning, and this pipe mode moved down right along with it, automatically, because the length is solved, not typed in. Around the crossover frequency, both drivers are making the same sound from two places 148 millimeters apart. Move off axis, and one path is longer than the other, and where that gap reaches half a wavelength, the two arrivals cancel. At 2 kHz, that's 0.86 wavelengths apart, the unavoidable compromise of pairing a 7-inch woofer with a 1-inch tweeter. When sound runs off the sharp edge of the front panel, the edge itself starts radiating, a fraction of a millisecond late. That late copy adds to the original at some frequencies and cancels at others, and the response goes bumpy. Rounding the baffle edge softens it. This cabinet's 18mm roundover cuts the ripple from 5.8 down to 4.9 decibels, peak to peak. The cabinet isn't carved from a block. It's built as a translam, 26 horizontal layers of 18mm board, CNC-cut and stacked. That constraint runs deep. A stack of flat layers can quantize a wall thickness, but it can't cut a circle. So the driver openings aren't in the layers at all. The stack is cut solid across both drivers, and the true round bores are sawn through after assembly. A separate 6mm face panel, milled in one setup, carries the real apertures and doubles as the flush mount recess for both drivers. The crossover was fitted the same way, not typed from a textbook filter, but solved. Measured driver data goes into a circuit solver. An optimizer searches for component values that flatten the summed response and hold the impedance above 3 ohms. The result? An acoustic crossover near 2 kHz, 4th order, 85 decibels of sensitivity, and a 31 decibel null when the tweeter is wired in reverse. Evidence the two drivers are actually summing in phase, not just overlapping. It's a design candidate built from manufacturer data, not yet a measured result. And the design doc says exactly what to measure and in what order before it's called finished. None of this is trusted blind. A self-test suite checks every model, circuit solver, box alignment, diffraction against known analytic answers. And after the geometry is built, a separate script probes the actual solid to confirm the corner traps' mouths are really open and the cabinet is watertight everywhere else. What comes out the other end is a cabinet where every dimension has a reason, a port length that's solved, not guessed. Corner traps that cost almost nothing because they follow the grain of how the thing gets built. A crossover fitted to the drivers actually measured, not the ones on a spec sheet. Human judgment set the goals. The agent did the arithmetic, checked its own work, and this is where it landed. D365 Tartu 2W. Designed in collaboration with Claude. Every number in this video is in the repository, and every model that produced it runs again on request,